Hello friends, dear student, this is second video in connection with the first video which is related to analysis of determinate structure, and I am Dr. N.S. Naik from the Department of Structural Engineering, Sanjani College of Engineering, Kopargaon. So here in this video we will continue with the introduction topic of analysis of determinate structure. So let us take a recap. In the first video, we have already discussed about the definition of structure. What is meant by structure? Again, I am repeating the definition. Structure is an assembly of members connected to each other with the help of joints, and which can support, means this assembly can support the external load. So any sort of construction which consists of different elements connected to each other with the help of joints and supporting the external load can be called as structure. We have already discussed idealization of structure, means its classification, what is meant by discrete system, what is meant by continuum system, and what is meant by hybrid system. In addition to that, we have already discussed about skeletal structures or framed structures. Now we will discuss few more terms which are related to our subject, or rather we must know before starting the actual contents of our subject. So let us start with types of joints. So how joint can be defined? Joint is the interconnection of members, or it is a point where two or more members are connected to each other. So in structural engineering, we are using different types of joints. So what are the types of joints which you will come across while studying this particular subject? So first one is pinned joint. The second is rigid joint. Third one is internal hinge. Fourth one is internal roller, and at the end free end. So let us start with pinned joint. The joint which offers no restraint, means no resistance to rotation, is called as pinned joint. Pinned joint can transfer forces only. It cannot resist movement, and hence it is called as non-moment resisting joint. Since the joint cannot resist movement, the members at this joint are free to rotate. Now, before discussing the joint, we must know the cause-effect relationship. Cause-effect relationship means if you apply a moment is a cause, then its effect is rotation. Now here, this is pin joint. And this is bracket, a pin is inserted, and this is the supporting object or say member. Now see, if you apply a moment to this end, this is anti-clockwise moment. Now what will happen? If you apply a moment like this, the member will rotate about this joint in the same direction as that of moment. Why? Because the joint is not offering any resistance to this applied moment. If I fix this joint with the help of weld, if I weld this member to the joint, then the member will not rotate. Because in this case, if the joint is welded, this joint will offer resistance to the moment in opposite direction. If moment is anti-clockwise, the resistance offered by the weld will be in opposite direction. But this is pin joint, and it permits the rotation of member about this pin. So this is the characteristic of pin joint. If you draw free body diagram of pin joint, Then this is vertical reaction at the pin and this is horizontal reaction at the pin. Remember, there is no moment. There is no moment offered by the joint. This is reaction moment. There is no moment at the joint. Moment 0. So only two unknowns are there, AX and AY. Right? This is again a figure with the help of which we can discuss the behavior of pinned joint. So two members are connected at joint. So this green dot, it shows a pin and these two members, blue color members, are connected to this joint. The initial angle between these two members is 90 degree. And now I am applying a moment in anti-clockwise direction. Now since the pin joint, it permits the free rotation or free movement of the members, what will happen now? This member, first member, will move to new position shown by dotted line, and hence this is rotation of first member. Similarly, the second member will occupy the new position because of this moment. This moment is in clockwise direction, so members are also rotating in clockwise direction. So this dotted line, it shows the position of second member. So theta 1 is rotation of first member, theta 2 is rotation of the second member. Remember here, theta 1 is not equal to theta 2. Theta 1 is not equal to theta 2. So members are free to rotate at pin joint. Pin joint, it may permit, or at pin joint there may be translation in x direction and in y direction. Particularly in case of plane structures, the joint may have translation in x direction and translation in y direction. Okay, so this is typical behavior of pin joint. Members are free to rotate. The angle between the two members after rotation is not equal to 90 degree. So this is behavior of pin joint. Now let us move to the next type of joint, that is rigid joint. The joint which rotates as a whole is called as rigid joint. The joint which rotates as a whole is called as rigid joint. This joint can transfer forces as well as moments. In short, this joint offers resistance to the external moment. Hence it is called as moment resisting joint. This figure shows a rigid joint. So this member is connected, member number 1 is connected to this column, second member. Okay, now if you apply some moment at this end, beam or member number 1 will not rotate because immediately the joint will offer resistance to this moment. Resistance to this moment. This joint rotates as a whole, means what happens, see, this is again a joint. Let us say this is a rigid joint. This figure shows behavior of a rigid joint. So first member, a blue color line, and this is the second member. Now moment in clockwise direction is applied at this rigid joint. Now what will happen? This first member will occupy new position, and now this is rotation of first member. At the same time, the second member will occupy new position, and this is rotation of the second member. But now in this case, theta 1 is equal to theta 2. It means that the joint rotates as a whole. This is rigid joint. The angle between the two members remains 90 degree even after the rotation. So this is the difference between the pin joint and the rigid joint. So this is typical behavior of rigid joint. At this joint, there may be translation in x and y direction. There is no relative rotation, but a single rotation is there. So at rigid joint only one rotation is possible and that can be denoted by theta. While at pin joint there are two rotations, two independent rotations of the members, theta 1 and theta 2. But here there is no relative rotation, only one rotation is there, that is theta. Theta 1 is equal to theta 2 is equal to theta. The joint rotate as a whole and the angle between the members remain constant even after loading or even after application of the moment. So in this way we can differentiate between the rigid joint and the pin joint. Now next joint is internal hinge. Internal hinge is considered as a joint when inserted in a beam. So here a hinge is inserted in a parabolic arch. This is internal hinge. In case of a beam, this is internal hinge. This hinge is inserted in the beam. Displacement conditions at internal hinge are the same as that of hinged joint. Okay. If internal hinge is inserted in a beam connecting two members, so here two members are connected. This is the first member and this is the second member. And these two members are connected to each other with the help of joint, and this joint is hinge joint, internal hinge. What is the advantage of this internal hinge? We can develop one additional equilibrium equation, that is zero moment at the point of hinge. So let us discuss it. Now let us consider this beam. This beam is having three supports, or say three support reactions, R1, R2 and R3. Now if I ask you to calculate these three reactions, then we are having three equilibrium equations. Summation fx is equal to 0, summation fy is equal to 0 and summation m is equal to 0. Now the first equation, that is summation fx is equal to 0, is of no use because there is no load acting in inclined direction or in horizontal direction on the beam. Beams are mainly designed to support vertical loads. So here we can use only two equations, that is summation fy is equal to 0, summation fy is equal to 0, and the third equation summation m is equal to 0, summation m is equal to 0. Now with the help of these two equations alone, because summation f now fx we are not going to use, with the help of these two equations alone, it is not possible to calculate these three unknowns. We need at least three equations. Now here at this stage we can develop additional equation. Since hinge is there, we can write one more equation, summation m about this hinge, about point A is equal to 0, and thus using summation fy is equal to 0, general equation summation m is equal to 0, and one additional equation summation m about hinge is equal to 0, we can develop three equations and we can find these three unknowns, R1, R2 and R3. Okay. Now next joint is internal roller. Internal roller, when inserted in a beam, is considered as a joint. When internal roller is there, there are two equilibrium equations we can use, namely sum of forces in the plane of roller equal to 0 and moment at the point of insertion of roller is equal to 0. Thus, in addition to the conventional three equilibrium equations, we can develop two more equations, that is sum of forces in the plane of roller is equal to 0 and moment at the point of insertion, or summation m at the point of insertion of roller is equal to 0, and thus we can solve the indeterminate problems. Indeterminate problem means where number of unknown reactions are more than the available equilibrium equations. Okay. So here again, if you consider this continuous beam or this compound beam, how many reactions are there? Vertical reaction is there at fixed end. This is horizontal reaction. This is moment, and here again two reactions will be there. So total count is 1, 2, 3, 4 and 5. So let us forget about summation fx is equal to 0. We are having two equilibrium equations. Summation fx is equal to 0. Summation fy is equal to 0 and summation m is equal to 0. In addition to that, if we develop two more equations, we can solve this problem. So at internal roller we can develop two additional equilibrium equations. Sum of forces in the plane of roller is equal to 0 and moment at the point of insertion is equal to 0. Okay. Now let us consider the last joint, that is free end. Now sometimes free end is also considered as a joint in structural analysis. So this is about the types of joints. Now based on the analysis or the method of analysis, how structures can be classified. Determinate structure. What is mean by determinate structure? A structure which can be analyzed using conditions of equilibrium alone is called as determinate structure. For example, here I will take one example. For example, I am having a beam which is supported on roller at one end and the second end is supported on hinge support. Second support is hinged support and carrying some load. Now if I ask you to analyze the beam or to find the support reactions, then definitely you will draw free body diagram. This is support A, this is support B, right? And this is reaction at A. Let us name this reaction as VA. And this is hinge support. So there will be two reactions, VB and HB. This is HB. This procedure we are following in engineering mechanics, VB, or mechanics of solids. So there are three unknown reactions. Now this problem can be solved using three conditions of equilibrium alone. So first condition is summation fx is equal to 0. If you apply this condition, summation fx is equal to 0, you will be having answer hb is equal to 0 because there is no load acting in horizontal direction. hb is equal to 0. If you apply summation fy is equal to 0, in that case you can develop one equation in terms of VA and VB. That equation will be VA plus VB is equal to W. Now only two unknowns are remaining, so two equations are enough to solve the problem. VA plus VB is equal to W. And when you write or when you use the third condition, summation M, sum of moments about support A or B, any support you can select, is equal to 0, then you can find VB. If you are taking moment about A, you can find VB, and after knowing VB, from this equation you can calculate VA, and thus the problem can be solved. So this problem can be solved using conditions of equilibrium alone. Hence, this problem is a determinate problem and the structure is determinate structure. The structure is determinate structure. Now, we will discuss one more example. Let us consider a plain truss. Let us consider a plain truss supported and loaded as shown. So this is, say, roller support, or we will consider it as hinge support, and here this is the roller support. Okay, now let us calculate the support reactions. Draw free body diagram. So first reaction is vertical, second is horizontal. At roller support only one reaction will be there. Okay, only one reaction will be there. Say this is VB, this is VA. It will act in downward direction. You can assume any direction. If you assume upward direction, and you will get negative answer, and then you can reverse the direction of reaction. Here I am selecting the correct direction, and this is HB, sorry, HA. So there are three unknown reactions. If you apply summation Fx is equal to 0, you will have an answer HA is equal to P. So one reaction is known. Summation Fy is equal to 0 plus Vb minus Va is equal to 0, and thus you will be having relation Va is equal to Vb. Va is equal to Vb. And now only one unknown is remaining, therefore. And we will use third condition, summation M is equal to 0, and we can calculate Vb or Va. And thus the problem can be solved using conditions of equilibrium alone. So this is determinate structure. This is determinate structure. Of course, determinate structure may be determinate externally or internally. That is different part. We will discuss it in continuation with basic definitions. Presently I am talking about reactions only. If suppose we add one more member here, then the type of structure will be different. That we will discuss in continuation with the basic discussion. But determinate structure means which can be analyzed using conditions of equilibrium alone. Which can be analyzed using conditions of equilibrium alone. For example, if we will consider a structure like this. Now, this is a first support which is hinged. This is the second support which is hinged. Load P is acting as shown, and now let us try to calculate the reactions. Two reactions at A, two reactions at B, because both are pinned support. So total reactions are 1, 2, 3 and 4, and we are having only 3 equilibrium equations. So problem cannot be solved, and without knowing the reactions we cannot analyze this particular structure. Okay, so it cannot be solved using conditions of equilibrium alone, and such type of structures are called as indeterminate structure. A structure which cannot be analyzed by using conditions of equilibrium alone is called as indeterminate structure. Is called as indeterminate structure. To analyze such structures, we have to develop additional equation, and that equation is called as compatibility equation. Indeterminate structures are also called as redundant structures. For example, let us take one simple example of a propped cantilever beam. So this is a beam fixed at A, this is free end B, and at B the beam is supported on roller. The beam is supported on roller like this. Now if I give you a simple beam like this, cantilever AB carrying some load, say 10 kilonewton, and if I ask you to find the support reactions, easily you can calculate the support reactions here, and you can plot SFD and BMD. So this can be analyzed using conditions of equilibrium alone. But in this case, what will happen? Now if you draw free body diagram, first reaction, second, since this is fixed beam, fixed support, M and VP. So how many reactions are there? There are 4 reactions. Through summation Fx, we can write HA is equal to 0. Still there are 3 reactions, and now the remaining equilibrium equations are 2 in number. So problem cannot be solved using conditions of equilibrium alone, because now we are having 3 unknowns and 2 equilibrium equations. Hence the problem is indeterminate and the structure is called as indeterminate structure. So this is propped cantilever. Propped cantilever is indeterminate structure. Which cannot be analyzed using conditions of equilibrium alone. Now to solve this problem, we need one more additional equation, and that equation is called as compatibility. Equation, and here we need VB, that is force. So we can develop compatibility equation in terms of displacement, that we will learn in the next subject, second subject. Here I can develop a equation using condition vertical displacement at B is equal to 0, and now I am having 2 equilibrium equation, 1 compatibility equation, 3 equations, 3 unknowns. I can solve this problem. So to solve indeterminate problem, we need additional equation. That equation is called as compatibility equation. Let us take one more example. Now I will consider again a simple frame carrying a horizontal load supported on hinged support at say A, and there is a roller at B. But here I will add one more member, A, B, say C and D. Now what will happen? See, if it is asked to calculate the reactions, now there is one reaction in vertical direction, VA. There will be second reaction in the horizontal direction. Let us name this reaction as HA. There is one vertical reaction at B. We can name it as VB. So now we are having 3 equations. 3 unknowns. VA, VB and HA. Using three conditions of equilibrium, we can find these unknowns. We can find HA, we can find VA, we can find VP. But after that, if I ask you to calculate forces in all these members, you cannot find the forces. If you consider equilibrium or method of joint, if you consider joint A, there are three members connected to each other. If you consider joint D, three members are there. At C, three members are there. At B, three members are there. And in method of joint, we can analyze truss with method of joint when there are two members connected to each other, means when there are two unknowns. But here at each joint there are three unknowns. So the analysis cannot be completed using conditions of equilibrium alone. So different methods are there to find such unknowns or to analyze such structures that we will discuss in the analysis of indeterminate structures. Here the scope of subject is limited to analysis of determinate structures only. But now this structure is indeterminate structure. Analysis cannot be completed with conditions of equilibrium alone. Hence, let us discuss degree of static indeterminacy. What is meant by degree of static indeterminacy? A statically indeterminate structure. Just we have discussed about indeterminate structure. A statically indeterminate structure is said to have a degree of static indeterminacy or of degree of redundancy. So degree of static indeterminacy is also called as degree of redundancy. A degree of static indeterminacy is the number of unknown reactions. See, the number of unknown reactions and internal forces in excess of available equilibrium equations. The degree of static indeterminacy can be studied in two ways: degree of internal indeterminacy and degree of external indeterminacy. So here the structure is internally indeterminate because we cannot find the forces in members. We can find the reactions but we cannot find the internal forces, and hence degree of internal indeterminacy and degree of external indeterminacy. So this structure is externally determinate. We can calculate the reactions. But we cannot find the internal forces. So internally indeterminate, externally determinate, and hence the degree of internal indeterminacy and degree of external indeterminacy. Okay. Degree of internal indeterminacy is denoted by DSI with I as suffix, and degree of external indeterminacy with suffix E, external. Degree of internal indeterminacy is related to internal unknown forces. Means internal unknown forces means these forces, internal forces. While the degree of external indeterminacy is related to external forces, that is reactions. So let us discuss today the degree of external indeterminacy. It is related to the reactions of a structure and is equal to number of support reactions in excess of available equilibrium equations. And hence equation can be written like this: degree of static indeterminacy external is equal to R minus available equilibrium equations, where R is number of unknown reactions. Now, if you consider this structure, there are four unknown reactions. Okay. Now, according to our formula, degree of static indeterminacy external is equal to R, number of reactions, minus available equilibrium equations. Now here the available equilibrium equations are three. Summation fx is equal to 0, summation fy is equal to 0 and summation m is equal to 0. So I will write minus 3 is equal to, how many unknown reactions are there? 1, 2, 3 and 4. So 4 reactions are there. So R is equal to 4 minus 3. The answer is 1 and hence this structure is statically indeterminate externally, and the degree of static indeterminacy external is equal to 1 if only three unknowns are there, three unknown reactions are there, then R minus 3 is equal to 0. Then we can call it as externally determinate. Degree of external indeterminacy is equal to 0, 3 minus 3. Now here degree of static indeterminacy, of course external, I am talking about external degree of indeterminacy, is equal to R minus available equilibrium equations. Available equilibrium equations, I will write in short EE. Okay, R means how many reactions are there? Unknown reactions R1, R2, R3. So unknown reactions are 3. Available equilibrium equations are, already we have discussed in case of a beam, we are not considering the first equilibrium condition, that is summation fx is equal to 0 because load is horizontal. So only now we are having two equations with us, summation fy is equal to 0 and summation m is equal to 0. Two equations, three unknowns. But since there is a hinge, we can write one more equation in addition to two equilibrium equations. Remember now this equation I am not considering. These two equations are there, 1, 2, plus I can write one more equation. Zero moment at the point of hinge. So I can write summation m at the point of hinge, let us suffix h, is equal to 0. And now I am having available equilibrium equations 3 in numbers, and hence degree of external indeterminacy is 0. So this structure is determinate structure. This structure is determinate structure. Okay, same is the case with the arch which is shown here. Now for this structure, see how many reactions are there? HA, VA, HB, VB, 4. Okay, we are having three equilibrium equations plus one additional equation which we can develop because of the internal hinge. Moment at crown is equal to 0, 1, hence equal to 4. Available equilibrium equations are 4 and the reactions are 4. Available equilibrium equations 4. So this structure is statically determinate externally and the degree of static indeterminacy external is equal to 0, and thus we can use this particular formula. Degree of static indeterminacy external is equal to R minus available equilibrium equations. Here also first unknown, second unknown, third, fourth, fifth. Let us ignore summation fx is equal to 0. Degree of static indeterminacy external is equal to R minus available equilibrium equations. Okay. Now number of reactions are, ignore these horizontal reactions, 1, 2, 3. Available equilibrium equations are now 2 in numbers because summation fx is ignored, and hence this structure is indeterminate externally and the degree of static indeterminacy is equal to 1. This is Propt cantilever. This is Propt cantilever. Similarly, you can consider different structures and you can calculate the degree of static indeterminacy. The degree of static indeterminacy. Here the degree of static indeterminacy is 0 because 3 reactions are there. R minus 3 available, R minus 3 available equilibrium equations, degree of static indeterminacy is equal to 0. In this case, degree of static indeterminacy is equal to 1, and like this. So thus we can calculate the degree of static indeterminacy external for indeterminate structure, or before analyzing a structure we have to calculate degree of static indeterminacy external as well as internal. So about the internal degree of static indeterminacy we will discuss later on. So at present this is about degree of static indeterminacy external. Thank you.